talking about a few of the states. Since we talked about one specific state last chapter, what state was that? Gas. Gas. So it would make sense that we're going to talk about probably solids and liquids in this chapter. So, here we go. I gave you kind of an abridged version of your typical properties of solids. I didn't give you like a big, long, wordy, six-postulate kinetic molecular theory like I did for gases. Okay, so here are just kind of your typical properties that you're going to see for solids. All of these should be relatively common sense, I feel like. You guys probably know that solids are not easily compressed. Yes? Yes. You guys probably know that they don't diffuse very well. You probably know that if they're extremely compressed, they have a high density. That's not new, correct? Okay. You also probably knew that solids expand with temperature. Do you guys know that?
Yep.
You guys know that that's why they have to
gases.
What?
Gases expand.
Well, all things are going to expand with temperature. I can't think of any.
Water. It's opposite somehow.
Somehow. I just think that's amazing because it had to be that way.
Yeah, because of the fish.
Because otherwise, all the fish would die, and which would completely change the ecosystem, which would probably kill life on Earth.
Yeah. Still think we can't explain it today. We can't explain why it happens.
Yeah. Like it's also, why does water have such a high specific heat capacity? What I mean by that is why does it take so much energy to raise the temperature of water? Well, God didn't make it that way. We'd probably overheat on Earth.
Real quick, and fish would cook.
Yeah. Because a lot of the energy that the sun produces and hits the Earth gets absorbed by the water.
And it makes it worse when you swim in water. Because for your sunburn, because water.
Yeah, it's reflective.
Yeah. Yep. I mean, it makes sense. If you got a sunburn, just don't go outside. Okay. Last one up here. I think you probably know this, but it may not be completely obvious because when you look at this desk, it doesn't appear to be vibrating. But I'm hoping you guys will know that solid particles are always vibrating. And why do we know they're always vibrating?
So ridiculous.
The subatomic particles are always moving.
And how do we know they're always moving? I mean,
Science.
solid has
Energy.
Zero.
Well, it's not yet. What did you say?
Energy.
Energy. Okay. We know that solids have the lowest energy, but they still have energy, correct? So if they still have energy, they're probably going to be moving. Okay. So yes, solid particles are always vibrating. And we cannot assume, because if they didn't have any energy,
They would
They
die.
wouldn't be able to.
I don't even know. You
Would they be able to
would create you create a black hole. Let's just say that.
That's probably
All right, here we go. We're going to talk about two types of solids.
Crystal.
Okay, we're going to talk about the crystal version and then a different type of solid. What a crystalline solid is, as you can probably imagine, is where you've got your particles that make up that solid that are nicely repeatable, their patterns is nice, all of the bonds are the same length and same distance. I think I shared this with you, but bond length relates to energy.
These always be ionic.
Yeah. There are covalent bonds that are crystalline.
Like diamond.
Yeah. Well, that's a network covalent. But yeah, water is a crystalline solid. Ice is a crystalline solid.
Ice.
Yep. Yeah, ice water. Sorry if a lot of times when I say water, everyone assumes liquid, I suppose. But yeah, a solid water is a crystalline solid. Okay. Now, it's not just ionic that forms these nice crystalline solids. If you have a covalent substance that forms a solid that has a nice repeatable pattern and that has all the bond lengths and bond strengths the same, it's a crystalline solid. Okay? Very repeatable. Okay? There's a lot of different structures within a crystalline solid, but very repeatable pattern. Salt would be one, sugar, right? You probably look at sugar and go, that doesn't look like a crystal. Well, if you looked at it under a microscope, it would have a very nice crystal pattern. And sugar is covalent, right? Second type, amorphous. Anybody know what paraffin is?
Dolphins have
Paraffin.
what?
It's wax. Yeah, it's like the chemical name for wax. Okay? Second type is amorphous. It's a solid it's a solid that actually has no repeatable pattern. You've got no order. You've got bond lengths and bond strengths that are all over the place. And you can see by this visual, all of the bonds are different lengths. Okay, so that actually considerably changes its properties, which we're going to talk about some of those properties today. How crystalline solids act a little bit differently than amorphous solids do. All right, and part of the reason why wax is amorphous and has all these different bond lengths and bond strengths, like this is a longer bond, this is a shorter bond. Usually the longer the bond is, the weaker it is. The shorter the bond is, the stronger it is. Okay? And the reason why this happens is wax actually solidifies really quickly. So it doesn't have enough time to order its molecules in a way that it's ordered. Okay? What's really interesting is, I don't know if you guys remember the lab we did at the beginning of the year when we did melting point and freezing point of water. Do you remember that?
Yeah.
Okay? And what we did was, we had our graph where it went down and then it went like this. Everybody remember the graph of this? And this is where it was cooling, and then it would drop below the freezing point, went back up and froze. This here, the reason why it goes below the freezing point is because it has to get in an orderly pattern. And so it actually gets below the freezing point while it's trying to order itself in a way that's a nice crystalline pattern. And then it releases energy back up to the freezing point and freezes. Kind of interesting.
I don't know.
Really?
Yeah.
You probably won't have the graph on there, but...
I did a doodle.
Oh yeah, there it is. Yep. Okay? So, big difference. Crystalline and amorphous. The number one thing I want you to get out of crystalline's ordered, amorphous is not ordered. We'll talk about the property effects that has. This, probably why did you show me this? I don't know. Probably didn't need to. You guys know what melting is, right? Hopefully. Let's start.
Just in case you were.
Just in case you forgot. I think we did this in chapter 2 when we talked about this, and I actually gave you all the phase changes, and I gave it to you in like a matching easy multiple choice section or something like that, and a lot of you got it wrong. So here it is again. And most of you probably know what melting is. Most of you probably know what freezing is. Most of you probably know what boiling is. It's sublimation, it's condensation, it's those things that maybe are a little bit more tricky. But. Oops. Have you seen this? Have I showed you a heating curve before?
Yeah, physical science.
I know I did a lot in physical science, so I'm just going to quickly use this to quickly review. I'm pretty sure we talked about this also in chapter 2 when we were doing those labs. I mean, that was essentially a heating curve. Okay, and this is of water. And what you notice is at 0 degrees, you either freeze or melt. At 100 degrees, you either boil or condense. Now, do you remember way back in chapter 2 there were 2 types of heat? You remember what those 2 types of heat are? It's a long time ago.
Thermal?
Good guess.
Except for the
No.
One starts with an L, one starts with an S.
Oh.
Latent
Latent
and
Snake.
one that makes.
I know one of them is.
One of them really makes
sensible.
sensible.
Oh,
Sensible.
yeah. One of them makes it go into another phase. One of it.
Okay?
One of it stays.
So these two places that I've circled are your latent heat.
Okay.
And if you remember, latent heat is heat where you're going from a phase to one phase to another. It's during a phase change. And if you remember, latent heat, you never see a what change? No, you will see a phase change.
See a temperature change.
You're not going to see a temperature change. And you can see that on the graph, the temperature change while it was going from a solid to a liquid or from a liquid to a gas. Did it? The temperature change? No.
Oh, temperature change. No.
No.
Temperature.
Okay? And then the parts where you have a slope, here, here, and here, that was the sensible heat. And if you remember, I said this is the type of heat that makes sense. Most of the time when we experience adding energy, we usually experience a temperature change, correct? Or if you remove energy, you usually see a decrease in its temperature. All right? Now, I'm not going to elaborate anymore on that. We spent a lot of time talking about that earlier. Just a quick little review. The reason why that's brought up is because the type of solid that you have actually determines or changes the way those heating curves look because of the property differences. Crystalline solids have nice exact melting points because all their bonds are the same length and strength. Or it says exact melting points. What does that mean?
It doesn't matter how much you have.
Okay.
Just
You're starting to get a little comfy there, Gage.
exactly.
Leaning back. What does it mean here when I say exact melting points?
Well, at a certain temperature,
That
it
lady
get that.
thing.
Okay. So when it says exact, it means when it hits this temperature, all of it will melt at that temperature.
Yeah.
Does that make sense? Okay? You're not going to see some of it melt at 10 degrees, and then some of it melt at 12 degrees, and then some of it melt at 15 degrees, and then some of it melt. You know what I'm saying? It all melts at one temperature, an exact temperature. And this should make sense. If I go back to the visual of this, if all of these bond lengths are exactly the same, they have the same amount of energy, correct? Does that make sense to you? If they all have the same length, they're going to have the same amount of energy, which means at a given temperature, they will all break at the same time.
But the whole substance has to be the same.
Yes, we wouldn't assume that. Okay? So because they are all nicely ordered, perfectly repeatable pattern, perfect order, what happens is when you add energy and get to its melting point, it all breaks at the same temperature because all the energy of each bond is exactly the same. Well, how do you think that's going to affect the amorphous type thing?
Someone's gonna melt some point.
So amorphous is going to melt, freeze, boil, condense, not all at the exact same temperature. And the reason why is because are all the bonds exactly the same? No. And so what you have is the weaker bonds will break first or at a lower temperature, and then the temperature will have to increase a little bit to break the stronger bonds. Does that make sense? Okay, so what you see with crystalline is it will melt, boil, freeze, all that stuff at a rigid temperature, one temperature, all happens at that temperature. But for amorphous, because you've got different bond lengths, different bond strengths, they actually will melt over a temperature range. So this is what a crystalline curve would look like. An amorphous curve, you'd probably see something like this, but then you might see kind of like a small slope while it's melting or freezing. And then a slight slope here as well. Why is there a slight slope during the phase change?
Because all the bonds are breaking.
Yeah, all the bonds are breaking at different temperatures, because you have different strengths of those bonds. The weak ones break first, temperature goes up to break the stronger ones. All right? Oops. So, last thing, we're done. We'll be done 10 minutes early today, guys. How's that sound? We can take a little nap. I just threw these in here again, just because they're probably the most often forgotten or least talked about phase changes. You've got your sublimation and your deposition. Sublimation is probably one that we're probably more familiar than deposition, and that's going straight from a what to a what? Solid to a gas. Example, dry ice, or solid CO2 that goes straight to the vapor phase. And deposition is the opposite when you've got a gas that goes directly to a solid. This happens in the atmosphere when you get snow. Okay, like what I mean by that is the gas doesn't turn into a liquid and then the liquid into a snowflake. It goes straight from the gas to the snowflake. Called deposition. Okay, now, do we see that happening? No, but that's what happens. Okay. So again, just two phase changes. I want to get these up here so that you're a little bit more familiar with them. They completely bypass what phase? Both of them. The liquid phase. All right, any last questions?